video, we're going to be going over an example related to forces in 3D systems. I'll let you pause the video so you can read over the question and attempt the question on your own if you want. So, in the question, we have a cable that is connected to a telephone pole at point B, exerting a force of 140 newtons towards point C. We're told to find the moment of the force at the base at A, using scalar approach. Since point A is a fixed support, we can call the moment force at the base MRA, the moment reaction force at point A. We will assume positive is going in these directions. So, let's start by writing out the coordinates for points A, B, and C. Point A is located at the base with coordinates 0, 0, and 0 meters. Point B has coordinates 0, 0, and 6 meters. And point C has coordinates 2, -3, 0 meters. In the second step, we're going to find the force vector BC. Recall, force vector BC can be found in the form of its magnitude times a unit vector in the direction of the vector we're trying to find. So, we know that the tension force is exerted from B to C. So in this case, we can write the force vector BC as a product of the magnitude times a unit vector that goes from B to C. Remember, to find the unit vector BC, we can just find the position vector from B to C, divided by the magnitude of the position vector. To find position vector BC, it is simply the coordinates of point C minus the coordinates of point B, and we get this. To find the magnitude of the position vector, we just square each value here, add it together, and square root the whole thing to give us 7 meters. We can plug the values we just found into our force vector BC equation. Note that the magnitude of force BC is given to us in the question. It is equal to 140 newtons. So, once we plug everything in, we get our force vector BC. In this third step, we're going to find moment about the x, y, and z axis. First, we're going to take the x, y, and z force components from this force vector equation, because since we want to do this question using a scalar approach, we'll need the force components to analyze the moments about each axis. Let's draw the force components out. Note that the y and z components are negative, and that just indicates the direction of the forces. Now we can analyze the moments about each axis. For the moment about the x-axis, we only have Fy creating a moment about the x-axis, so we get mx equals to positive Fy times Rz, because it creates a positive moment. Rz is the distance from the force to the xy plane, which is 6 meters. And we get a moment about the x-axis equal to 360 Newton meters. The moment about the y-axis can be expressed as Fx times Rz, because Fx is the only force contributing to the moment about the y-axis, and is creating a positive moment. And the moment about the y-axis will equal to 240 Newton meters. For the moment about the z-axis, none of these forces contribute to a moment about the z-axis, so mz equals to 0 Newton meters. With our moment components, we can put it into component form to give us the moment vector at A. Now, in step 4, since we have the moment vector at A, we can find the magnitude of the moment at A, which is also the reaction moment at A, MRA. To find the magnitude of a vector, all we do is square each x, y, and z moment component, add them together, and square root the whole thing. And we're left with the moment at base A is equal to 433 Newton meters. That concludes the example for forces in 3D systems. In the next video, we'll be looking at 3D equilibrium, specifically free body diagrams in 3D systems.